Hello students, welcome to the lecture on Relational Model Data Structure, and after this completion, we will be able to learn the following objectives. Understand the concept of information processing, discuss about attributes and relations, explain the applications of MIS, describe the structure of a relational model, and understand the concept of traditional set operation. Let us start with the relational model. The relational model is not the first implementation data model. Prior to that were the network data model exemplified by Codacil and the hierarchical model implemented by IBM's IMS002E. Also of historical interest, when object-oriented programming gained prominence, there were many attempts to replace a relational database with an object database, but generally they did not fare well. The relational model is centered on this idea: the organization of data into collections of two-dimensional tables called relations. We can also think of the relational model as a generalization of the set data model, extending binary relations to relations of arbitrary arity, features of the relational model. Conceptually simple, the fundamentals are intuitive and easy to pick up. Powerful underlying theory. The relational model is the only database model that is powered by formal mathematics, which results in excellent dividends when developing database algorithms and techniques. Easy to use database language. Though not formally part of the relational model, part of its success is due to SQL, the de facto language for working with relational databases. Relational model concepts. The data is represented in tables in which each row gives data about a specific object or set of objects, and rows with uniform structure and intended meaning are grouped into tables. Queries allow the extraction of information from the tables. A fundamental feature of virtually all relational query languages is that the result of a query is also a table or collection of tables. Each table is called a relation and it has a name. Example, movies. The columns also have names called attributes. Example, title. Each line in a table is a tuple or record. The entries of tuples are taken from sets of constants called domains that include, for example, the sets of integers, strings, and Boolean values. The relational model uses a notion of relation that is closely related to this set theoretic definition but differs in some details. In the relational model, information is stored in tables. A domain is a named set of scalar values, all of the same type. A domain is a data type. When we create a domain, we must specify which type of domain we want to use. A range domain specifies a valid range of values for a numeric attribute. When creating a range domain, we enter a minimum and maximum valid value. A coded value domain can apply to any type of attribute text, numeric, date, and so on. Coded value domains specify a valid set of values for an attribute. A relation R on a collection of domains D1, D2 to Dn consists of two parts, a heading and a body. The heading consists of a fixed set of attribute domain pairs. A1 is to D1, A2 is to D2, and so on till AN, DN. The heading is also called the schema. The body consists of a time-varying set of tuples where each tuple consists of a set of attribute value pairs. A1 is to VI1, A2 is to VI2, till AN is to VIN, and I is equal to 1, 2 to M. The body is also called the instance. Base relations. The real relations, called base table in SQL. Views, the virtual relations. A view is a named derived relation. Snapshots. A snapshot is a real, not virtual, named derived relation. Query results. The final output relation from a specified query. It may not be named and has no permanent existence. Temporary relations. A non-permanent named derived relation. Relational algebra. It is useful to express such queries in language that is much higher level than C, in the sense that the query expresses what we want. Example, all tuples with coarse component equal to CS101 without having to deal with issues such as lookup in indexes as a C program would. For this purpose, a language called relational algebra has been developed. In relational algebra, the operands are relations. As in other algebras, operands can be either constants, specific relation in this case, or variables representing unknown relations. However, whether a variable or a constant, each operand has a specific scheme, list of attributes naming its columns. The first three operators we shall use are common set operations: union, intersection, and set difference. We place one difference on the operands of these operators. The schemes of the two operands must be the same. The scheme of the result is then naturally taken to be the scheme of either argument. Let's take an example first to understand this concept. We have frequently wanted to extract from a relation tuples meeting certain conditions, such as all tuples from the course student ID grade relation that have course component CS101. For this purpose, we write the selection operator sigma C in bracket R, where sigma, Greek lowercase sigma, is the symbol for selection, C is the condition, and R is the relation operand. The condition C is allowed to have operands that are attributes from the scheme of R as well as constants, whereas the selection operator makes a copy of the relation with some rows deleted. We often want to make a copy in which some columns are eliminated. For that purpose, we have the projection operator represented by the symbol pi. Like selection, the projection operator takes a single relation as argument, and it also takes a parameter, which is a list of attributes chosen from the scheme of the relation, that is the argument. Combines attributes of two relations into one. R3 is equal to join R1 D1 R2 D2. Given a domain from each relation, join considers all possible pairs of tuples from the two relations, and if their values for the chosen domains are equal, it adds a tuple to the result containing all the attributes of both tuples, discarding the duplicate domain D2. The union of two relations A and B is the set of all tuples belonging to either A or B or both. Example, A is equal to the set of employees whose department is SW development. B is equal to the set of employee whose age is less than 30 years. A union B is equal to the set of employees who are either in SW development department or having age less than 30 years. The intersection of two relations A and B is the set of all tuples T belonging to both A and B. Example, A is equal to the set of employees whose department is SW development. B is equal to the set of employee whose age is less than 30 years. A intersection B is equal to the set of employees who are in SW development department having age less than 30 years. The difference between two relations A and B in that order is the set of all tuples belonging to A and not to B. Example, A is equal to the set of employees whose department is SW development. B is equal to the set of employees whose age is less than 30 years. A minus B is equal to the set of employees whose department is SW development and not having age less than 30 years. The Cartesian product of two relations A and B is the set of all tuples T such that T is the concatenation of a tuple A belonging to A and a tuple B belonging to B. The concatenation of a tuple A is equal to A1 AM and tuple B is equal to BM plus 1 to BM plus N. In that order is the tuple T is equal to A1 to AM, B1 plus 1 to BM plus N. Example: A is equal to the set of employees whose department is SW development. B is equal to the set of employee whose age is less than 30 years. A times B is equal to is the set of all possible employee number department IDS pairs. The selection operator yields a horizontal subset of a given relation, that is, the subset of tuples within the given relation for which a specified predicate is satisfied. The predicate is expressed as a Boolean combination of terms, each term being the projection yields a vertical subset of a given relation, that is, the subset obtained by selecting specified attributes in a specified left to right order and then eliminating duplicate tuples within the attributes selected. Commercial implementations of the relational model extend relational algebra by introducing some additional operations. If R is a relation, using the back definition, sigma R denotes the relation obtained from R by eliminating all but one copy of each tuple. Aggregation operators allow operations such as find the sum or average of the elements in a single column of a relation, count the number of entries in a relation or a column of a relation. Grouping produces a new relation whose entries may be the result of an aggregation operation. For example, from a relation enroll, student SSN, CRN, credit hours, we can produce relations EI, student SSN, number of courses taken by grouping on student SSN. Consider the projection operator pi L in bracket R. L is a subset of the attributes of R. We can extend the projection operator by allowing L to include functions of the attributes of R. That is, new attributes are created which are derived from R. Since a relation is a set or a bag, there is no ordering defined for a relation. That is, two relations are the same if they contain the same tuples irrespective of ordering. The outer join operator addresses the fact that some tuples in a relation are not represented in a natural join involving the relation. This is because there is no matching tuple in the relation being joined. Primary storage structures for relations. In terms of the general insert, delete and lookup operations that are helped are those where the domain value is specified. A binary search tree with a less than relation on domain values to guide the placement of tuples can serve to facilitate operations in which a domain value is specified. An array used as a characteristic vector with domain values as the array index can sometimes serve. A hash table in which we hash domain values to find buckets will serve. In principle, a linked list of tuples is a candidate structure. We shall ignore this possibility since it does not facilitate operations of any sort. Modification of the database. XSB provides an array of features for modifying the dynamic database. Using Assert1, Clauses can be asserted using first argument indexing in a manner that is now standard to Prolog implementations. While this is the default behavior for XSP, other behavior can be specified using the executable directives index3 and index2. For instance, dynamic clauses can be declared to have multiple or joint indexes, while this indexing can be either hash-based, as is typical in Prolog systems, or based on tries. Furthermore, the size of any index table expands dynamically as clauses are asserted. Adds a dynamic clause to the database. Clause must be of one of the forms, head or head, body. Note that because of the precedence of 2, using the second form requires an extra set of parentheses. Assert, head, body. Default, first argument indexing. If the index specification for the predicate is not tries, this predicate adds a dynamic clause to the database before any other clauses for the same predicate currently in the database. If the index specification for the predicate is not tries, this predicate adds a dynamic clause to the database after any other clauses for the same predicate currently in the database. It removes through backtracking all clauses in the database that match with clause. Clause must be of one of the forms, head or head, body. Note that because of the precedence of 2, using the second form requires an extra set of parentheses. Retract, head, body. Space is reclaimed when a clause is retracted. It removes every clause in the database whose head matches with head. The predicate whose clauses have been retracted retains the dynamic property. Predicate retractall, one is determinate and always succeeds. The term head is not further instantiated by this call. It removes the definition of the specified predicate. PredSpec is of the form pred arity. Everything about the abolished predicate is completely forgotten by the system, including the dynamic property. There is also an abolish by 2 which takes pred and arity as its two arguments. It returns through backtracking all dynamic clauses in the database whose head matches head and body matches body. For facts, the body is true. It performs just as retract 1 does, except that it does not reclaim the space used by the retracted clause. This is provided to allow programmers to modify dynamic clauses while executing them, a practice that is discouraged. It runs through the dynamic code for the predicate indicated by head and reclaims space for any clauses that have been deleted from that predicate by retract nr1. In general, XSP supports hash-based indexing on alternate arguments or combinations of arguments along with trie-based indexing. Static predicates. In this case, IndexSpec must be a non-negative integer which indicates the argument on which an index is to be constructed. If IndexSpec is 0, then no index is kept, possibly an efficient strategy for predicates with only 1 or 2 clauses. To insert a tuple t, we examine the bucket to check that t is not already there, and we create a new cell on the bucket's list for t if it is not. To delete tuples that match a specification x, we find the domain value from x, hash to find the proper bucket, and run down the list for this bucket, deleting each tuple that matches the specification x. To look up tuples according to a specification x, we again find the domain value from x and hash that value to find the proper bucket. We run down the list for that bucket, producing as an answer each tuple on the list that matches the specification X. If the operation does not specify the domain value, we are not so fortunate. An insert operation always specifies the inserted tuple completely, but a delete or lookup might not. Navigation among relations. The power of the relational model can be seen well when we consider operations that require us to navigate or jump from one relation to another. Since there is so much difference between the times taken when the condition is true and when it is false, we should be careful how we analyze the for loop of lines 1 to 6. That is, instead of counting the number of times around the loop and multiplying by the greatest time the body can take, we should consider separately the two outcomes of the test at line 2. First, we go around the loop n times because that is the number of different values of t. For the k tuples t on which the test at line 2 is true, we take om time each, or a total of okm time. For the remaining n to k tuples for which the test is false, we take O1 time per tuple, or O n minus k total. With the right indexes, we can answer the same query in OK average time, that is O1 time if k the number of students with the name C. Brown is 1. That makes sense, since all we must do is examine two k tuples k from each of the two relations. The indexes allow us to focus on the needed tuples in O1, average time for each tuple, if a hash table with the right number of buckets is used. Summary. Now in the end, let us summarize what we have learnt in this lecture. Database information stored over a long period of time in a computer system, and for database management systems, the software that allows people to store, access and modify this information. Updates consist of transformations of the tables by addition, removal or modification of rows. Commercial implementations of the relational model extend relational algebra by introducing some additional operations. An array used as a characteristic vector with domain values as the array index can sometimes serve. XSB provides an array of features for modifying the dynamic database.